Hello there, Math 126 students. Thank you for someone asking this on the discussion board. They're asking about this optimization question. So I'm going to use this mostly as a chance to review optimization. I do want to say if you're worried about applied optimization, my promise is that anything you see on the test will be similar to something you saw in the homework. Here's what you saw in the homework. So we're going to flip through it and then we'll do this problem. So you saw shortest distance. So that's something I could ask. You saw minimum surface area. You saw question 12, which is the same as the one you're asking me about here. And so that was maximum volume. And then we have minimum cost, minimum surface area. So minimum surface area, minimum cost, maximum volume, minimum surface area, minimum distance, minimum distance. I'm going to only ask you one of those things, so know those well. Okay, so let's talk about this one. The key principle is, what are we optimizing? And it's volume. So this is a perfect example of what I was talking about in class, which is identify what you're optimizing and write that first. What we're trying to do is find a two-variable function for that so we can take partial derivatives and find the critical points. And on my midterm, I promise that I usually don't ask this step anymore about using the second derivative test because I'll probably ask that somewhere else. And so usually on an applied problem now, my style is to say, set up the function, find the critical point, and stop. But anyways, what is the volume? The volume of this box is x times y times z. The key thing is this point, this xyz point, is a point on here, is what they're saying. And as we talked about in class, the question doesn't make sense until you have a constraint. Because if you're trying to make the volume as big as possible, you make x, y, and z as big as possible. And there is no maximum. What's the constraint? The constraint is you have to be under there. It's easier for me to draw things like this in 2D. We had an almost identical problem in Math 124 where we said you're allowed to draw boxes under here. What's the biggest rectangle you can draw? Where this point is going. So we're doing the 3D version of that. Okay, so the constraint is that x, y, and z have to come from here. And that leads to something you can easily substitute. So you get z is equal to 12 minus 4x minus 3y. And again, if you want more practice, this actually is directly from the homework as well. It just might have looked different here. I was trying to think, when I wrote this question, I was trying to help by giving a picture. They didn't give a picture in the homework. Okay, so we've done it. We have a two-variable function for volume. It's going to be xy times all of this. Now, I personally would expand, so let's do that now. So I'm going to do xy times this. So it's going to be 12 xy minus 4 x squared y. So we're multiplying each term by xy. Minus 3 xy squared. Now, the rest of the problem is going to be a fairly standard take the derivative, find the critical points. So to me, the guiding principle is, what are you trying to optimize? Volume. What are the constraints that x, y, and z have to satisfy this? And from that, you get this two-variable function. But let's run through the rest since we're studying for the test. Partial with respect to x is 12y minus 8xy minus 3y squared. We want to know when that's 0. Simultaneously, we want to know when this is 0, which is going to be 12x minus 4x squared minus 6xy equals 0. Now, there is a tip here, which is that whenever possible, factor first. Don't just blindly start solving. And both of these can be nicely factored. So it's definitely the next thing I would do is I'd rewrite the first one as, let's say I can factor out a y. So it's 12 minus 8x minus 3y equals 0. And then factoring out, looks like I can factor out a 2x. 6 minus 2x minus 3y is 0. Double check that I haven't gone off the screen. Okay, we're doing good. Then we're going to solve. Now, there are two possibilities from both of these. One is that y could be 0. The other is that 12 minus 8x minus 3y is 0. Similarly, from this one, we could say x equals 0 or 6 minus 2x minus 3y is 0. But since we're trying to find the volume of the biggest box, it's not going to be these ones, where x is the box that's underneath there. So I don't need to find, those are critical points I can start finding, but I don't need to. Okay, that's the advantage of it being an applied problem. So now I can combine more easily. So let's start with equation 1 and solve for, let's say let's solve for y. So I get 3y equals, so I move this to the other side, so it's 12 minus 8x. And the truth is, what I'm doing I think it's suboptimal. But if you're someone that's, an optimal way to do this, actually, now that I look at it, is to subtract them side by side and get 6 minus 6x plus 0 equals 0. And that's because I saw that you could subtract side by side and get that. And so then I get x is 1. That's going to be faster. But if that's a little bit of adaptation. If you're following the standard method I've been teaching where you substitute, that also will work. You take this, you shove it in here, you solving it x is 1. And then you can plug it back in and you get, and we'll check solutions here in a second. I mean, I'm not checking solutions as I go. I don't want to post a video that has a typo in here, but so this is going to be 4 thirds. And then lastly, we get z is this. So x is 1. This is 4 thirds. Did they ask for the dimensions? Find the dimensions. Yes, that's what I'm doing. So z is going to be 12 minus 4 minus 4. 12 minus 8, so z is 4. Okay. Well, I don't think I have the solutions ready here. Let's just pull it up. We'll go here. Oops, my archive. Winter 2008. I clicked on exam 1. Darn fool. All right. So there we go. That's what we got. Now, on this exam, I did ask for the second derivative test. So let's do that for the practice. So the second derivative test, let's try it out. Partial with respect to x twice is going to be negative 8y. Partial with respect to y twice is going to be with respect to y twice is negative 6x. And the mixed partial, xy, is 12 minus 8x minus 6y. And you can check the other one with respect to x. Make sure you get the same thing. And we're going to plug in our values. So f of x at 1 comma 4 thirds. That's the value we're checking. You get, so we're plugging in 4 thirds, so it's going to be negative 32 thirds. F of yy at 1 4 thirds is negative 6. So it's concave down in 2 directions. That's good because we're looking for a maximum, but we need to make sure the mixed partial isn't too big. So at this value, we get 12 minus 8. This times 4/3 is minus 8. So I'm a little worried because it looks kind of big. That's going to be negative. This is negative 4. Let's see if it's big enough. So we're going to compute D. D is negative 32/3 times negative 6. And then we're doing minus negative 4 squared. Now, if I do that, it's 64 minus 16, which is positive, which is good news. If D is positive, then the concavity doesn't change. It's concave down in all directions. So it is indeed a local max. All right, let me know if you have follow-up questions on that. But hopefully we've answered the idea of if it's going to be an applied optimization question, it's going to be one of those 4 things you saw in the homework. And this was one of those 4 things. All right.